So now we're going to write a Python script to create some functions for our bubble and dew temperature and pressures for a mixture of benzene and toluene. And then we're also going to make some plots at a constant temperature and a constant pressure. So the very first, well, before we even get started coding anything, I just went ahead and copy and pasted our normal imports. Today we're going to be using the root function scipy-optimize to solve for the dew and bubble temperatures. And then we have some of our other regular imports related to plotting, as well as our CHE toolkit. So the very first thing we need to do is bring in our CHE props, if it'll let me. And again, we are going to be using benzene and toluene. And the thing we're going to be using from this is the saturation vapor pressure, like we mentioned before. Looks like that's all right. So the very first thing we can do is go ahead and define our equation for bubble pressure, which I have pulled up on our the right side of the screen here. Actually, that's the dew pressure. There we go. So right here is our, actually down here is our bubble pressure. The sum of the mole components and the liquid phase times the saturation vapor pressure for each component. So in this case, we're going to be making a function called bubble, second time I've done that, bubble pressure. And we want to pass in two things. We're going to pass in the constant temperature that it's going to be at. And we're also going to pass in a vector because later on we're going to be using a root. But the vector is just going to be the mole fractions for benzene and for toluene in the liquid phase. So in this case, we're going to have, we'll just pass it in as x, and then our temperature. And we don't need to do any math inside of it. All we need to do is define our return. And we want the sum of our x's times the saturation vapor pressure for that specific substance. Simply forgot a colon. Should be good now. All right, and then from there we can also make our bubble temperature. And it's going to be a super similar process when it comes to doing the same thing for the dew, just with slightly different equations. So in this case, our dew temperature is going to be, as you see on the right side of the screen here, I'm pointing, but you can't see me point. This is our equation here. And we want to find the root at which point this equals 0. So within our bubble temperature equation, we're going to pass in, once again, the mole fraction and liquid phase, but this time we're going to pass in pressure instead of temperature. And we want to end up returning this equation on the right side over here. I don't know if you can hear that, but there's some loud noises outside my window. But we want to end up returning the root of this equation, which will give us the bubble temperature. So for now, we'll just supply it with some equation, and then we need to supply it with an initial guess for the temperature, and then it will start there and iteratively guess up or down until it reaches the point where it's either really close to 0 or exactly 0. So in this case, we'll just supply it with a guess of 25 degrees Celsius, and then we're just going to want the first return, the first element of the actual roots that this function here returns. And now we just need to define our equation. But you'll notice that for this equation here to work over on this right-hand side, we need to know the temperature. So within our equation, we can actually define another equation. And we're just going to have a single input, a single vector. And in this case, our vector is going to be, it's going to have one element. And the reason we need to define this as a vector is because the root function, that's how it takes its arguments. So in this case, it's going to be plugging in this initial guess into our equation v here, or yeah, into our equation, and then finding the root of that. And then our actual equation is just going to be using our bubble pressure. Sorry, I blanked out there. So the bubble pressure of x and then t. And then we want to return, actually more accurately, it'd be better to move this return up here. Return our bubble pressure of x, t, and then minus our pressure. And actually we want to return this as a vector, and we can go ahead and do the same thing for our due pressure and our due temperature, just with slightly different equations. So actually I'm honestly just going to copy and paste this. Go ahead and run that. But this time we're going to be doing our due pressure. And this time we're going to be passing in a value for the vapor phase. And it's going to be a similar equation, but in reality we want to return 1 divided by the sum of y divided by the pVap of that specific element. All right, and then from there, sorry, I blanked again. We want to copy and paste the same thing as before. But this time we're going to be using the due pressure instead of the bubble pressure, and we're going to be passing in y. Really, we could just leave it as x as long as we used it the right way, but obviously that's not a great way to go about things. A small note, I was accidentally using a different variable than temperature in these pVap things, but that's good now. So now we can go ahead and start making our arrays that we're going to be using to plot. And the very first thing we're going to do is we're going to define something called Z1. And the reason we're calling it Z1 is, you know what, I'm going to call it something other than Z1. I'll call it C1 for component. Yeah, I'll just call it C1. So C1 is going to be a linearly spaced list from 0 to 1, 11 elements. And the reason we're calling it C1 instead of X or Y is because C1 is always going, or we're going to be using basically the same values to refer to both the mole fraction of vapor and the mole fraction of liquid. So it doesn't really matter how we define it, as long as we can keep track of it in our code. And C2 is going to be the liquid or vapor component of the other element, or of the other substance. So we're going to do 1 minus C1. And if we just want to take a look at this, so there are two arrays, and as you can see, they're opposites of each other. So now we want to make, oh, didn't mean to do that. So now our end goal is to make a list of our bubble pressures. And for now, I'll just make a blank list so we can come back to that. But our bubble pressures are pretty simple to calculate. We have a temperature, so we're going to go ahead and define that. In this case, it's going to be 393 Kelvin. And while I'm at it, I'm just going to define our pressure. It's going to be 150,000 pascals. We're not going to be using the pressure quite yet, but we will later on. So we have our temperature, and then we know we can find our saturation vapor pressure by our pvap function at T. And if we want to take a look at our saturation vapor pressure, should have printed it. Maybe I messed that up. So this is for benzene, and then this is for toluene. So if we want to take the value for benzene, we'll just take the first element, and if we want to take it for toluene, we'll take the second element. Let me make sure I have that in the right order. Yep, benzene and then toluene. And our bubble pressure list is just simply going to be, actually I can probably maximize this. It's just going to be our component of x1 times the p set, and we want our first element, so index 0, and then our second element is going to be our second component times the second index of our saturation pressure. Accidentally did x1 and c1. See, that's how I'm thinking of it in my head, the liquid phase and the vapor phase. So maybe calling it c1 and c2 is cause more problems than it's worth. So now we can do a similar thing for our dew pressure. And actually, let me give that its own box here just to keep things a little more organized. But once again, we can do a similar thing for the dew pressure. And if we want to think about this in a way more broadly, I guess, if we want to make a list of each of our components, our liquid or vapor phase components of each substance in the mixture of benzene and toluene, we can make an array comprised of our C1 and our C2, and this should give us an array with 2 columns. That might just be an error with my syntax. 1 second. So there we go. So here you can see that this is our, I lied about the 2 columns, it's actually 2 rows. But this is going to be our C1 and then our C2. And then this can be either our liquid or our vapor phase components, but in this case it's going to be our vapor phase. So we're going to be making a list of our dew pressures. And we'll start out with an empty list. And for each of these elements in our array here, we want to take the dew pressure. And let me redefine this. We're going to find the dew pressure with our input of y and our temperatures. I'm going to figure out this error and I will come right back. So I figured out my issue. Basically, I was trying to be a little too fancy with it. But we're going to say for each element in our C1, in this case we'll call it, sorry about that, syntax, but for each element in our C1, and in this case it's just going to be y, so we'll just call it y. We want to do the same calculation where we're putting it into our dew pressure equation and then adding it to our list. So here we can define y2 as 1 minus y1 again, and then y equals an array of those 2 values. I can't remember the syntax for doing this. It seems I need to plug in my computer. I believe I need those brackets there. And then we want to calculate the due pressure for each of those combined set of y and y1 and y2. So we'll pass in our y array and our temperature. Let's see what happens here. All right, and then we're actually going to append this due pressure to our due p list. I'm gonna have to double check on the syntax of this. You know what? I'll just do it while we're here. I see. So we need to move this inside our parentheses here. Here we go. So now we can go ahead and plot these, but we'll go ahead and do the temperatures first. And basically we're going to make a plot of the bubble and due pressure, and then the bubble and due temperature at our given pressures and temperatures, and then we can see how the curve interacts. So I found a small error that was making it extremely difficult to get my plots working, so I'll go ahead and run through this again. I should probably run that. But basically, I had a comma instead of a plus. Okay, so we're going to be making a figure. And we're going to make some subplots, and we're going to do this on one plot. So we'll do it with one row and two columns. And we'll title these plots. Constant T and constant P. Right, and so our first subplot, or our first scatter plot, I should say, we'll do the pressures first. So we have our X is going to be our component plot. Our Y is going to be our bubble P list. And then our row will be row 1, column 1. And the title will be, well, we'll leave it untitled for now. And then we can do the same thing for our due pressures. There we go. So this is our bubble pressures, and then these are due pressures. And then we can do the exact same thing for our temperatures. Oh, accidentally opened a new tab there. And it's going to mess everything up because it's plotted on the same thing. And obviously our pressures our temperatures are going to be much smaller than our pressures. All right, so in a minute I will go over what this is, but this is our bubble pressure, our dew pressure, our bubble temperature, I believe. No, sorry, this is our dew temperature and then our bubble temperature. All right, so just quickly interpret these. So this is our diagram for our mixture of benzene and toluene. Let me make sure I have that in the right order. Yeah, benzene and then toluene. So as we increase the ratio of toluene to benzene, you can see that the bubble pressure goes up as well as the dew pressure. And obviously, like we saw in our notes, the dew pressure is always going to be lower than the bubble pressure, just based on the PV diagram. And it's a similar story, just the reverse. Our dew temperature is always going to be higher than our bubble temperature for our mixture. And as you decrease the temperature, as you increase the ratio of toluene to benzene, the bubble and dew temperatures both decrease.